Alright, here we are in section 2.6. We're wrapping up now our chapter on linear equations, and here's where we get to include the inequalities. And you'll notice this section is called Solving Linear Inequalities. The difference between what we've been doing in chapter 2 with solving linear equations is now we're going to have that in there, that inequality. So what is an inequality? Well, instead of seeing an equal sign, you're going to see one of these four. You're going to see a greater than, or a greater than or equal to, or a less than, or a less than or equal to. So this first one reads greater than. The next one is greater than or equal to. The next one reads less than. And the last one is less than or equal to. The extra line underneath indicates that you have the potential to be equal to the other side as well, not just being greater than or less than. So you'll start 2.6 with several problems. Some of them that just ask you to graph them on the number line, and then a set that asks you to express the solution set in interval notation, and that's probably the new piece that's being added. You might remember graphing on a number line. We're going to step up the graphing on the number line using symbols that maybe you aren't as used to. I know I was taught to do a closed dot and open dot. So it used to be that a closed dot would be used for less than or equal to or greater than or equal to, and an open dot for less than or greater than. And they would call those closed or open. We still call them closed or open, but we use symbols that will help us then be ready to do interval notation. So let's look at some examples so we can make that very clear. Let's look at number 2 here. The inequality they give us is x greater than -3. So the way you'd read that is x is greater than -3. Okay. And some of you might remember the whole alligator deal, where the alligator likes to eat the bigger number. Okay, for some reason that's one of the math things that tends to stick. I don't know what our human fascination is with crocodiles and alligators, but it's there. For whatever the reason, we're fascinated. So when we're told in math that there's an alligator and it wants to eat the bigger number, we hold on to that knowledge. We don't ever forget it. So in this case, this does not include 3. Include the value -3, I should say. Okay? It does not include it. It's all values that are greater than -3. Okay? So it's all values greater than -3. And greater than means to the right of the number line as we head to the right from that value. So to graph this on a number line, what that would look like as we draw this here. Now that I am in the habit of always putting 0 as a reference, just so I can kind of get my bearings here. But -3 would be right here, and we want all values to the right of -3. So here would be the negative end, here would be the positive on the right, and you would shade, how you graph it on a number line would be to visually show how far this goes. So we would shade it. Some book versions, instead of using a different color, they might do a line up above it. Okay, going across. That would also indicate that those are the values you're taking with. And we are headed to positive infinity here. This is positive infinity. This is negative infinity. As we go all the way to the left, all the way to the right. And then how you represent not including -3 is going to be using a parentheses. So when it does not include something, use the parentheses. Okay? So parentheses for does not include the number. Okay? And then we'll do a, and that's what's called an open. Okay, we go all the way up to -3, and then we stop. We include everything but -3. Now, what does that mean for interval notation? It's basically where you remove the number line and write what you see. Interval notation is a way to be able to type the description here using math symbols only. So instead of using the words x is greater than -3, instead of using the symbols, the inequality symbols, interval notation is a way to show what's happening on the number line without having to draw in the number line itself. So what it's saying is that you're going to go from -3 to positive infinity, so you put your two endpoints of the group of solutions, or the set of solutions, which means all the values that will work for x. And then you frame it in whatever you would here. So this is an open interval, okay? So this is open, does not include -3. So we used a parentheses on the number line, we used a parentheses on the interval. Then the question is, what do you use to represent infinity? Well, if a parentheses represents an open spot, then we would also use that for infinity, either positive or negative, because it's not an actual value. It goes on forever. So it's not closed here. This is an open as well. So it's always a parenthesis for positive or negative infinity. Okay, so you always use parentheses when you're doing interval notation. So it's a picture of the number line, able to type it out or write it out without having to draw the number line. So the values here go from -3, not including -3, that's what the parenthesis tells us, all the way to positive infinity. The comma represents, here's our starting point, here's our end point. And because infinity is not a value, we can't close that. We do an open. Because the closed are brackets. That's what we're going to use for closed. And we'll do that in the next example here. Let's look at number 8. Number 8 gives us the inequality x is less than or equal to 7.5. And what that means is, if we were to say that in words, that is x is less than, did I say greater? I hope not. Less than, let's get that right, less than or equal to 7.5. So all the values that would make this statement true are either less than or equal to 7.5. 7.5 would make this statement true. 0 would make this statement true. 3 would make this statement true. -201 would make this statement true. -3000.752 would make this true. All values less than or equal to 7.5 make this statement true. So this one includes 7.5. Includes the value 7.5 or 7.5. So what would that look like on a number line? So if we draw our number line here, and again, I always just put in 0 for reference. Here we are headed to positive infinity on the right, negative infinity on the left. And I've got 1, 2, 3, 4, 5, 6, 7, 8, and 7.5 lands right in between 7 and 8 there. And now I'm going to show visually on the number line all the possible solutions for x. So I know it's going to include 7.5, and again, you might have been taught that as a closed dot. That's how I was taught. But now we're going to start to become familiar with using closed and open symbols, and in mathematics, a parentheses and open symbol. So here's yet another use for parentheses, right? So they are very, very versatile. You really have to understand the context of what you're seeing. But in this case, it's a closed. So we use brackets for does include a number. So less than or equal to, greater than or equal to. It's known as a closed interval or a closed spot on the number line. It includes that. It includes all the numbers up to it and that number. Notice how I face the bracket in the direction of what I'm going to shade, because I'm including all the values less than or equal to 7.5. So I go to the left for less than. Okay. And let's write that up here too. To the right is greater than. So to the left is less than, to the right is greater than. And that's what the number line looks like. Now what the interval notation would be is, again, to remove that number line and you're going to replace the squiggles with a comma in between the two values, the two endpoints, okay? And then you will add parentheses or brackets depending on if it's a less than, greater than, or less than or equal, greater than or equal to, okay? And then you always use parentheses for positive and negative infinity. So you'll always use parentheses for positive infinity or negative infinity. So what do we have here? We have, instead of representing all the numbers in between, we'll put a comma here, but where are we going in between? We're going in between negative infinity and 7.5, and so this comma in between represents all the squiggle we see on the number line. It's all those values included in between. Now we need to close it off because it gets to include 7.5, but we can't include negative infinity, so we need to go ahead and make that an open interval because negative infinity is an idea, it's not an actual value where we can stop. This continues on forever. Just like if we are greater than or equal to negative 3, the decimals that approach negative 3, they go on forever. There's an infinite number of little teeny numbers leading up to negative 3. So it remains an open interval there. Okay, so that's what they look like for interval notation, graphing on a number line inequality. Just watch for the instructions on these opening sets because some of them ask you to do number line, some of them ask you number line and interval notation. I just wanted to show you all the examples together so you could kind of compare and get used to that. So bring those questions to class. I want to show you one more on the back of this page. Want to note that. So let's turn this over here. I'm going to make sure that I'm still in the screen. Okay, that puts me right about here. So let's do, this is on page, still that same page, page 170. Let's also do number 10 on here, and here's why. And it looks like this. Negative 3 is less than or equal to x is less than 6. Okay? And here's a great opportunity for you to ask yourself what's different about this problem. And this is what I really want you to develop the skill for. Okay? Because sometimes I try to do every example, like in this case I want to show you this on the notes. But sometimes I want you to take the starters that I give you in the notes or the class, and then you push yourself further. You make those little brain leaps, because that's going to make you that stronger learner. That's what you're getting out of this class. Whether you go on to further mathematics, or this is your stopping point, or you're close to your stopping point of mathematics with Math 65, being able to learn and take that leap from the introduction to the next step is going to be huge, and that will serve you well no matter whether you use this mathematics in your career or not, or in your life or not. That ability to push yourself beyond. And one of the ways to do that is to not panic when you see something different, but ask yourself what makes this look different. What makes it look different is the fact that there's two inequalities. Okay, so if we were to cover, and then you go, well, I wish there was only one, I'd know how to do it. I'd know how to write the number line, and I'd know how to write the interval notation based on the examples we just did. Okay, well, if I would know how to do it, whether I covered up one or not, then we should be able to make that leap of what we would do if we do see both, right? We would know what to do if x, this left side is x is less than 6. We would know what to do there. The number line for x is less than 6. Here's 0, here's 6, positive infinity, negative infinity. We're going to go less than, so we're not including 6, but we're going to go everything to the left. The interval notation would be from negative infinity, can't close that off, that's open, all the way up to 6, also open because it's just plain less than. Okay. Well, now let's look at what this other piece is, okay? But we're including this restriction. These are like restrictions on the solution here. We're saying, hey, x can be anything as long as it meets these requirements. It has to be less than 6, and it has to be greater than negative 3. This negative 3 less than or equal to x, that's saying the same thing as x is greater than or equal to negative 3. It's saying that x needs to land in between negative 3 and 6. Okay, so if we were at x is greater than negative 3 here, here's our negative 3 and 0 just for reference. And now we're going greater than or equal to that. We would include the 3 and we'd head off to the right, and the interval notation, the interval notation would be a closed bracket, negative 3 comma positive infinity, open bracket, because infinity can't be a closed value. It is a concept. It goes on forever. Okay, so now if we were to combine both of these together, if we were to line up these two requirements here, where would the true solutions fall? Well, if you look at that, we've got the negative 3, we've got 0, we've got 6, and if we include all the values less than 6, so here's my first line, and then we include all the values to the right of negative 3, including negative 3. So I'm going to go over that with a second color. And then what is the combination? What's the crossover? What is the one that combines or happens twice, right? Well, the combination of that would look like this on the number line. Here's negative 3, 0, positive 6. We would close it at negative 3, open it at 6, and take all the values in between. This is negative 3 is less than or equal to x is less than 6. And I bet I'm off screen, sorry. Let me pull that up a little bit here. So negative 3 is less than 0 is less than or equal to x is less than 6. So it's the combination of those two. Here's one number line to the left and one to the right. The combination of those two go together. And then our interval would look just like this. You'd have the bracket, negative 3, everything in between until you reach 6, and then the open parentheses. So it's everything's in between negative 3, including negative 3, all the way up to positive 6, but not including 6. Okay, so it's all values greater than negative 3, including negative 3, up to positive 6, but not including positive 6. So hopefully that helps with that. Again, bring those questions to class. We'll start the next video down at the bottom with a try there. So we will see you there on the bottom of page 1.